Okay, we're going to look at now how this trigonometric substitution fits into our process. So we've got some examples here to do some comparisons on. Let's start with the first one here. First thing we're going to do is look to see if it fits a basic form. Remember, the only non-fraction, or the only fraction that we have that's a basic rule is exactly 1 over x. So definitely not going to be a basic rule. U substitution, that actually looks pretty good. What would we let u be equal to? Well, u would be equal to 1 plus e to the 2x, which means the u prime that would go with that would be 2e to the 2x. So if I look at what I have here, let's see, I need a 2, no problem. I will multiply on the outside by the 1/2. Remember, anything on the outside will carry down. And what I get here is the u prime over u to the 1/2, which of course would bring up to the top as a u to the negative 1/2. And when we integrate u prime times u to the negative 1/2, we get u to the 1/2 over 1/2 all plus c. And then of course you're going to flip that bottom fraction, multiply and put back in your u, and so we simply get the square root, or 1 plus e to the 2x to the 1/2 all plus c. So really just a simple u substitution. Let's look at this next example, which looks very similar, but there's an issue with it. Let me explain what the issue is. Again, not a basic rule, because in order to be a basic rule, we can't have a fraction, no way to turn it into a non-fraction, and it's definitely not just a 1 over x. So this time, if we try to do a u substitution, of course I'd pick the same u, and I would need an e to the 2x on top, which I do not have. So we can't do that. It's definitely not a trigonometric integral of the form sine raised to a power, cosine raised to a power, and it doesn't look like an integration by parts where we have two separate and distinct functions that cannot be combined. So you notice at the bottom of your list on that first page, it'll show you the process, and the last two on the process deal with the inverse trigonometric forms and the trigonometric substitution. And so when we get to this point, and we've tried everything else, the deal about these two is that you would pick the a and the u exactly the same way. A is going to be whatever we have to square to get the number piece, which in this case is 1. U is whatever we have to square to get the function piece, and in this case, the u is simply e to the x. If you remember, when we do this, and we multiply an e to the x times an e to the x, we add the exponent. So that's how we get the e to the 2x. Well, if that's the u, then the u prime that goes with that is an e to the x. So the u prime here is e to the x. And if we look at this, this is actually an inverse trig form. It is actually the form of inverse sine of u over a all plus c. So in this case, I'm going to get the inverse sine of u, which is e to the x over 1, or simply e to the x all plus c. So again, much easier, quicker to do than a trigonometric substitution. Let's go ahead and look at our next example. And in our next example, it looks an awful lot like the last one. And as a matter of fact, we saw that we could not do a basic rule, couldn't do a u substitution, not a trigonometric, not an integration by parts. Again, we would pick the a to be the function, the number that we have to square to get that, and u would be the function piece, which is e to the x. Then, even though I do have the u prime on top, this does not qualify as one of my inverse trigonometric forms. If you look on the front of that sheet, I've given you the inverse trigonometric form, and the a squared plus u squared would be an inverse tangent, but not underneath that radical. So whether it's because it doesn't fit it because it's a plus, or even if it didn't have the u prime, it's not necessary to do a trigonometric substitution. In a trigonometric substitution, we simply need to have a radical with a squared minus u squared, a squared plus u squared, or u squared minus a squared. And as long as we have any of those, then we qualify. In this case, we have a squared plus u squared, so we're going to use the substitution that we let u equal to a tangent of theta, so that the radical of a squared plus u squared will be equal to a secant of theta. In this case, our u is e to the x, and that's going to be equal to 1 times the tangent of theta, so that the radical then, which is the square root of 1 plus e to the 2x, is equal to a secant of theta, or simply secant of theta. Now, in the second step, we need to find dx, and here's the problem with that. You have your original substitution, which was e to the x equal to the tangent of theta. Now, you cannot just start doing a derivative on this, because taking the derivative of this side is not just going to give you dx d theta. We've got to get this equation to be an x equal. And how do we do that? Well, anytime I want to unwrap a x from an exponential function, I just apply its inverse. That is, I apply the natural log to both sides. So we get the natural log of e to the x will be equal to the natural log of the tangent of theta. The natural log and the exponential are inverse functions, so they cancel each other out, and we get x is equal to the natural log of the tangent of theta. And now I can take the derivative of this with respect to theta. It's really not a difficult thing to do, because with a natural log, whatever you see here is what goes on the bottom, and the derivative of that thing, which is the secant squared of theta, goes on top. And then simply multiply both sides by d theta, and we get that dx is equal to secant squared over tangent times d theta. The third step is to go back to our original integral. Everywhere there's a simple e to the x, we put in tangent of theta. For the square root of 1 plus e to the 2x, we put in secant, and for dx, we put in the secant squared over tangent. So we get the integral of, we've got the e to the x on top, so that's a tangent of theta divided by the radical, which is a secant of theta, times dx, which is going to be the secant squared of theta over the tangent of theta d theta. And here the tangents cancel, and one of the secants cancel, so we wind up with just the integral then of the secant of theta d theta. And by definition, this will be equal to the natural log of the absolute value of the secant of theta plus the tangent of theta, all plus c. So again, let's go ahead and create our right triangle. And to do that, we're going to take whatever our initial substitution was, and that's not a big deal. Our initial substitution was that e to the x is equal to the tangent of theta, and that's the same thing as e to the x over 1. By definition, this was the opposite over the adjacent. So when I create my right triangle, letting one of those sides be theta, the opposite is e to the x, the adjacent is 1, and as I said before, I guarantee you that that third side is going to be your radical, and if you were to perform the Pythagorean theorem on this, this is exactly what you would get. So now if we take our answer, which we got the natural log of the absolute value of secant of theta plus tangent of theta, all plus c. By definition, the secant is the hypotenuse over the adjacent, and the tangent is the opposite over the adjacent. So we get the natural log of the absolute value of the hypotenuse over 1. So that is the square root of 1 plus e to the 2x plus the opposite over the adjacent, which is simply e to the x, all plus c. Okay, the last thing I want to do here is to look at some of these forms that we've gotten, and I just want to at least go through on what we would do for a process on these. So let's start with the first one. Not a basic rule, not going to be a u substitution, because the problem becomes if I let u be equal to 9 minus 4x squared, I need a negative 8x. Now I can turn that 2 into a negative 8, but I cannot get an x. So we're going to try for an inverse trigonometric form. In doing so, let's see, a is what we have to square to get the number piece, which in this case is 3. U is what I have to square to get the function piece, so that's going to be 2x. And I do see that I have my u prime on the top. And remember, it's not the fact, well, I mean, you have to have the u prime, but if at this point you fit one of your inverse trigonometric forms, you want to use that. Whether or not you have the u prime on the top makes no difference for trigonometric substitution, but we don't want to go through that long process if we don't need to. And as a matter of fact, this does look like one of your inverse trigonometric forms. It gives the inverse sign. And so when you integrate this, you would get the inverse sign of u, which is 2x over 3 all plus c. Now, on the next one, let's look at this. This looks like not a basic rule, but a u substitution might work out quite well. U is going to be equal to 9 minus 4x squared, which means the u prime here is going to be a negative 8x. And of course, I can turn that into a negative 8x by multiplying by negative 4 and a negative 1/4 on the outside. And then you can go through and work the rest of this and see that you will get a u substitution. Matter of fact, you've got u prime over u to the 1/2, bring it up to the top, and go ahead and integrate it. This next one, again, another good case of the same u substitution. This will be u to the 1/2. Again, you need the negative 4 here to multiply together, give you the negative 8x and negative 1/4 on the outside. There's your u prime. And this time, instead of integrating u prime times u to the negative 1/2, we're just going to integrate u prime times u to the positive 1/2. This next case here, again, these look very similar. Here, not a basic rule, not going to be a u substitution because I would let u be the 9 minus 4x squared, which means I need another x in there. Again, I can get that number, but I can't get the x. This is actually going to be either an inverse trig or a trig substitution. It's not going to be an inverse trig since all of the inverse trig are fractions, but again, we're going to pick the a and the u to be the same thing. A is going to be equal to 3. U is going to be equal to 2x. And again, you don't need a u prime when you are doing a inverse, or trigonometric, substitution. Here we are using a squared minus u squared, so we're going to use that first substitution. Again, I'll let you go through and work that. This last one, once again, is going to be either an inverse trig or a trig substitution. The reason being, not a basic rule. Not a u substitution because now we have too many x's. Not a trigonometric or an integration by parts, but once again, we can use the, actually it's not going to be an inverse trig, it's going to be a trigonometric substitution. Why is that? Well, the a here is equal to 3, the u here is equal to 2x, but I don't have just a u prime on the top, I have extra x's. So in that case, again, both of these would be a trigonometric substitution.